Okay, so let's pick it up where we had left off. Following the work of John Dalton and Mendeleev, there was an idea, which is that what exactly is inside the atom? Dalton suggested it was simply a solid ball. But a series of observations caused people to start to realize that that's probably not quite accurate. John or J.J. Thomson, an Englishman, began to do research on exactly the details of the atom itself. And what he did was he did experiments with what is called a cathode ray tube. And a cathode ray tube looked like the following. There was a tube, and the tube had nothing in it. It was a vacuum. There was no air or any kind of gas. And there was a strip which was fluorescent, which meant it would glow when there was charged particles moving over it. And so he hooked up an electrical flow across it. And you could see a glow show up on the background of the strip. Now in the lower left area, you'll notice that there is this line, this light green line going across, and that actually is the electrons flowing, which he didn't know about. He didn't know what it was, but he knew that there was these particles going by. And what he observed was when he put a magnet next to the cathode ray, that this beam would bend. And if a magnetic field can bend the beam, that meant that that beam was made of charged particles. And he was able to figure out that though that charged particle was an electron, and he could know it was charged negatively because when he placed the magnet near the beam, it bent a different direction. So because the beam was being deflected or changed by both electric and magnetic fields, he knew it had to be charged, and the direction that it was bending indicated that it was charged negatively. So he then proposes that there in fact are electrons, and that what was happening was electrons were being emanated from the cathode side of the cathode ray tube, and that when you subjected a magnetic field to it, you would bend it because the charged particles being attracted to the magnetic field. If you put it in an electric field where you put two poles, you would see that the electrons bent to the positive side of the electric field and away from the negative. Both of these are evidences that this particle called an electron had a negative charge. So he was actually able to indicate that it was negative. He also recognized it had to be a particle, and it wasn't some kind of wave, but it actually was an item, and this item or particle in fact could be changed. And he initially called these corpusculars or corpuscles, which meant at the time simply small particles. And he was actually able to determine what its mass was, which was actually, it should be 10 to the minus 8. It was a very, very small. And the reason he could figure this out was he could measure how much the beam bent by. And by knowing how much it bent, he could then calculate its overall mass. This is what was later on called electrons, and by then it was known it was negative, and they knew what the mass was. And he correctly suggested that it came from the gaseous atoms themselves, and that again was true. He felt that these electrons must be around the atoms, and that what was happening is these electrons were being stripped away from these atoms and being shot across the cathode ray tube. So this was an interesting buildup, because it seemed to indicate that instead of just being these solid, indivisible atoms, they in fact are made up of small items, that actually have particles, smaller particles, subatomic particles, actually work together to make this thing called an atom. And he eventually suggested a new model, that atoms were not a solid sphere, but something that he came to know as plum pudding. He was suggesting that there was this blob or sphere of positive charge, and that buried inside this positive charge or this positive field, there were these electrons. And the reason why the blob held together is that the positive outside sphere and the negative inside would be attracted to each other because they were opposite charges. He did not actually think it was a plum pudding in there, but simply referred to as a plum pudding model. So he was indicating that in fact the positive pudding, you could strip away the electrons outside, and this would form a positive ion when you removed the negative electrons to it. And of course it was the negative electrons, when they popped off, that created the beam that could be moved. It's rather remarkable to come up with and really be able to identify so much data with this model. No, there is not plum pudding that makes up an atom. However, he recognized that by removing the electrons, I have imbalance of charge, and it would form a positive ion overall. So he said, so where does the electron go? Of what use? And of course he was suggesting it doesn't go anywhere. It doesn't have any use to it without being in the plum pudding. Now that he was wrong on. But the model of positive and negative charges that make up an atom, that was pretty good. So what we see now is John Dalton's solid sphere. It's actually blocked out a little bit. It changed. It changed when new information came in from the cathode ray tube, and J.J. Thomson in 1903 suggests a new model, which is the plum pudding model. And of course the plum pudding model tastes very, very good. Now a new question came up, which is, what about this electron? How much charge does it have? What are the details? Let's get the model about plum pudding and get it more accurate. Well, electrons are kind of small things, and so to work with them is a bit rough. But a guy named Millikan figured it out. What he was able to do was determine how much of a charge was on the electron. J.J. Thomson figured out the mass, but Millikan was able to figure out the amount of charge. The amount of charge is also very, very small. It's 1.6 times 10 to the minus 19th coulombs. And then it gave rise to a much more accurate or precise description of the mass of the electron, which you see here, 9.1 times 10 negative 29th grams. A very small number indeed. But how did he pull this off? Well, what you see here is what's called the oil droplet experiment. Let's walk through it. He had an atomizer which had oil in it, and the atomizer dumped very, very small droplets of oil into the chamber. Now there was a plate which you see on top, and that plate had a small hole in it. And because there was a small hole in it, some of these very, very small droplets of oil could work their way through. Now what he was able to then do was, through the viewing microscope, he could see the oil droplets as they dropped down. And by knowing how quickly they dropped down, he could get an average size of the oil droplet. Now then what he did was, he, after figuring out the mass of the droplet based upon how quickly the droplet fell, he ionized the droplets. That is to say, he hit it with radiation and stripped away the electrons. Now those oil droplets have a charge to them. And so then what he does is he uses a positive and negatively charged plate, and he adds electricity to these two plates. He creates a electric field. And what he's able to do is he's able to cause the oil droplets that are now charged to become suspended. They're able to just hang in space because the droplets are charged because they lost their electrons, and the plates are allowed to hold that charged particle. And he knows he can hold it there by viewing it through the microscope. And by knowing the charge of the electric field, he's able to determine the overall charge of the electron that's in there. So it was quite an incredible event that he was able to figure this out. So after the work of Millikan, a new gentleman by Rutherford does a rather extraordinary experiment. This quote may not make much sense yet, but he did an experiment that shocked everybody. And what he did was he was able to find out what's inside an atom itself. And this became known as Rutherford's gold foil experiment. Interesting enough, he was from New Zealand, and what he found was that the inside core of an atom is very, very small and very, very hard. And he found that the nucleus was positively charged. And you may say, but wait a minute, what about the plum pudding? Well, Rutherford's work and data was able to show that there's error in the plum pudding model. Some of it was right, but some of it was wrong. And Rutherford's experiment was able to show that's not quite right, and he was able to get a more accurate description. And what he did was he used uranium, which is very radioactive, to produce positive alpha particles. And what he did was he aimed these alpha particles at gold foil. And he did so by drilling a hole in a lead block through which the particles can go through. And what he found was that since the gold atoms were evenly spread out on this foil, that was pretty clear because there was no holes there, he thought, well, of course, this whole thing should go through. But in fact, it wasn't that way. Let's take a look. So on the right is your source of these particles. And the lead block narrowed the beam out. And there's the gold foil in the middle. And what he thought would happen was, if this is a plum pudding, if there were these electrons sitting in this positive field, the plum pudding, then the alpha particles should just blast straight on through the plum pudding. But in fact, that's not what happened. In fact, you had ricocheting going on. And the alpha particles bounced off from the gold foil. But wait. A large amount of alpha particles did, in fact, go straight through the gold foil, like it was empty space. So it seemed like a large amount of the gold foil atoms was actually empty. And that's why the alpha particle beam went right through it. But some of it ricocheted off, indicating that there was this solid core to these atoms, and that core had to be really small. And it had to be small because it didn't ricochet that often, and in fact most of it went through. So these solid cores had to be very, very tiny and only occasionally got hit. Now this big donut or a horseshoe-shaped gray thing, that was a fluorescent screen. And that's where the alpha particles lit up when they got bounced off or went through, and that's how Rutherford knew that this thing had gone through. So this was his description. If in fact the plum pudding was right, then all the alpha particles should have passed straight through it. However, as you can see, there was some ricocheting going on, and that meant there had to be a very solid center that was involved with it. And that solid center, he recognized, had to be the nucleus. Inside that nucleus is where the protons and neutrons were, and that the electrons would make this cloud around the outside. Now it's important to realize that look how small that nucleus is compared to the overall size of the atom itself. So most of the atom is empty space or occupied by the electron cloud on the outside.
In the early 1900s, J.J. Thomson proposed that an atom was a uniform sphere of positively charged matter in which electrons were embedded. This model is sometimes called the plum pudding model. Electrons are embedded in a sphere of positive matter, similar to raisins in plum pudding. In 1910, Ernest Rutherford, Hans Geiger, and Ernest Marsden carried out experiments in which very thin foils of metal were used as targets for alpha particles emitted from a radioactive source. Click on what Rutherford expected to observe the results Rutherford expected based on Thomson's model of the atom.
We'll actually move on from there. So what happens is Rutherford in 1911 proposes a more accurate model of what goes on inside an atom and suggests that nearly all the mass is in the middle and that there is a positive charge to the middle. Now we're going to take a stop here, and so the video doesn't get too long, and look at the quantum mechanic model.